first video for section 8.4 quadratic functions and their graphs is going to look at graphing a quadratic equation when it is in its vertex form. The general layout for a quadratic in its vertex form would be f of x is equal to a times the quantity x minus h squared plus k. So some of this looks familiar, I would imagine. For example, we know that the h that we see here is going to tell you if you are going to move your graph left or right. The plus k we had looked at, we had noted that this, depending on what k is equal to, will move your graph up or down. The a is probably the newest thing in the mix that we've been looking at. So the a, again, is going to tell you if you have a vertical stretch or compression. Okay. So, in other words, is your parabola going to be fat or thin? Okay. So, what I want to note here is that A actually does play an additional role. So, if A is negative, then that means that the parabola opens down. So it kind of frowns. If the a, or your lead coefficient, is positive, then your parabola opens up. Okay? So we do have all this information that we're going to use in order to help us graph the parabola. So before I begin, recall that a parabola basically kind of has like this U shape to it. Okay. So the parent function, which I'm going to go ahead and do in orange, is f of x is equal to x squared. And recall that we can do a basic table of values, so going from -2 all the way to +2. And if we plug in these x values into the function, we get +4, +1, 0, 1, and then +4. So this creates our initial parabola. Okay, notice that the parabola is symmetric in appearance, or almost symmetric. There we go. Okay. So this is the shape that we should be seeing every time we graph a parabola. So for the example that we're going to work in, we're going to start off with f of x is equal to 2 times the quantity x minus 2 squared minus 1. So let's go ahead and start identifying things. Well, I know for instance that I'm going to move down 1 because it's a -1 on the outside. So here, note that I do have a -2 on the inside of the squaring that's contained in those grouping symbols or those parentheses. So in this case, remember that when it's inside the house, it's lying to you. So when you see a -2, you should think, okay, I'm going to move to the right 2. So essentially what this means is, starting at where your vertex is, I'm going to go to the right 2, and I'm going to go down 1. So here is where my new vertex is going to be located. Again, just as a refresher, a vertex is essentially where the parabola is going to bloom from. So as you can see, that's where it will start to open up in this case. So the 2 here is kind of not necessarily needed in a sense. It is going to tell you how fat or thin your parabola is going to be, but you don't necessarily need to use it directly in your calculations. What I would suggest doing, or what I would suggest trying to do first, is to find the Y-intercept. Okay, let's bring it back to something that's familiar to us. So recall that your Y-intercept would have a coordinate point that looked like so, where your x value is always 0 and your y value will depend on what happens when you plug 0 into the function. So if we put 0 into the function, in other words, if we replace every x that we see with a 0, we will get that using our order of operations, 0 minus 2 is negative 2. Then we would have 2 times negative 2 squared is going to give us a positive 4. 2 times 4 is 8. And then 8 minus 1 is 7. So our particular y-intercept for this problem is at 0, 7. So I'm going to make my points blue. So there's my vertex in blue. And I need to find 0, 7 on the graph. Okay. So this is actually all that I need in order to provide a rough sketch of the graph. The reason being is, note that the parabola is symmetrical. Okay. So right where the vertex is, not only is that where the parabola blooms, but that's also where you can fold the parabola in half. So as you can see here, if I went 2 points to the right and went up, so let's see here, if I'm on the x-axis, if I go 2 points to the right, and then if I went up 7 spots, then I would meet the mirrored image, or that mirrored point. And I actually have enough in order to make my parabola. So if I connect this, here's the rough sketch of my parabola. Okay, you do not need anything else just to provide the rough sketch. Okay, so as you can see, and maybe it's a little bit harder to see, but if you compare the parabola that I have in blue to the one in orange, it does look a little bit thinner, and that's because we are stretching by a factor of 2. Recall that a factor of 2 is going to make things fatter, or sorry, this is going to make things thinner, and then a factor of a fraction between the values of 0 and 1 is going to make your parabola fatter or more spread out. Okay, so let's take a look at another one, shall we? So let's take a look at, I'm going to go ahead and clear this off. Okay, so let's take a look at the following problem. Let's take a look at f of x is equal to 3x squared minus 3. And actually, let's do that. Okay, so note that this one is a little bit different. If you need to, you can always rewrite the problem a little bit so that it matches that general f of x is equal to a times x minus h squared plus k. So in this case, we could rewrite this as x minus 0 squared minus 3. Notice that the minus 3 in the problem was never included in any sort of parentheses. It was never inside the house, so that indicated that it was a vertical change. In other words, that it was moving up or down. So in this particular case, then, we know that we're not moving left or right, so no left or right movement. But we do have a minus 3 here, and that one's fairly easy to kind of pinpoint as to what you're doing. So here you would be saying, well, I know that this is going to go down 3. The fact that this 3 over here is positive is going to tell you that it's going to open up. Your parabola will open up. And also that the fact that it is 3, or in other words, because 3 is greater than 1, your parabola is going to look thinner. Okay? So from here, let's go ahead and generate a coordinate plane. And again, if you need to, feel free to hop onto Google and download some graph paper, or if you have some readily at hand, or if you are pretty good at drawing them by hand, the options are out there for the taking. Okay. So again, just to kind of keep the parent function here, I'm going to go ahead and graph it just so we can have some sort of comparison. The best I can. Hopefully that looks pretty symmetrical to you. So again, we can actually pinpoint the vertex just by looking at the vertex form. So since I'm not moving anywhere, that means that I've moved 0 places left or right. And since I'm moving down 3, my vertical is going to shift to -3. So hopefully that kind of makes sense. So I'm not moving from left to right, so I'm going to stay here, and I'm going to move down 3 units. So my new vertex is at 0, -3. Okay. So this is why it's called vertex form. It's called vertex form because basically once you identify how you're moving left or right and how you're moving up or down, you have your vertex. Whatever values you've indicated, they tell you what your vertex will be. So at this point, we would need to find 2 other points in order to help us out here. And really, you can kind of just pick some points in order to create something. So for example, I know that this is symmetrical, and I'm going to indicate it with a bright yellow line or a bright dashed line. So my line of symmetry ends up being right in here. In other words, that would be where I would go if I wanted to fold my parabola. Okay, so in this case, let's just pick 2 points that are equidistant away from the vertex or away from the axis of symmetry. So I'm going to go ahead and work with the following 2 points. I'm going to work with -2 and 2. And again, I'm not necessarily picking them because they are opposites of one another, but if you notice that 2 is 2 spaces to the right away from the vertex and the axis of symmetry, and -2 is exactly 2 spaces to the left of the axis of symmetry. So if we plug those in to our function, so in other words, if I try to find out what f of -2 is, that's going to give me the following, and I can evaluate. So this is 3 times -2, which is -2 squared. It's going to give me 4 minus 3, so this is 12 minus 3, which is also now going to give me 9. So I would be at -2, 9. So this is going to give me 1, 2, 3, 4, 5, 6, 7, 8, 9. So there is that point. And then again, if I do the same thing, if I now look at f of 2, watch what happens. And here's where that idea of symmetry is going to come in. So this is 3 times, again, 2 squared is 4. 3 times 4 is 12. And then 12 minus 3 gives me 9 again. So the fact that they're symmetric means that they will have the same output here. So that means that I can come over here and find 2, 9. And then I can connect those. And as you can see, again, it's a little wavy, but again, sorry, it's computers and human hands mashed together. They don't always make the greatest pairing. As we can see, we do have a parabola that does open up. It is thinner than the parent function that we were looking at. We did not move it left or right, but we did move it down 3. So the parabola that you see here in the purple color is the newly transformed graph. I hope that these were helpful. If you do have any feedback or any questions, please feel free to reach out to me.